Sir, you can start now, sir.
ನಮ್ಮ ಫೋಟೋ ಬರಲ್ಲ.
ಸ್ಟಾರ್ಟ್ ವಿಡಿಯೋ
ಸ್ಟಾರ್ಟ್ ವಿಡಿಯೋ ಫಸ್ಟ್
Sir, you can start now, sir.
Yeah, but students have not yet come. So I thought I will give them 2 minutes. 2 or 3 minutes. Is it okay, Kavita? Are you Kavita? Hello?
No, sir. This is Maya here, so no problem, sir.
You are Maya?
Sir.
Okay. Guraj.
Yes.
ಒಂದು 5 ನಿಮಿಷ ಬಿಟ್ಟು ನೋಡೋಣ ಏನಪ್ಪ.
Okay, sir. Okay, sir.
See whether anybody is interested. So once I got a sample from moon stone, then that also we analyze on PPB levels. So it's very exciting.
Usually all the samples you do in nitric matrix.
Definitely, yes. Because chloride interferes, temperature interferes more serious. Best to go for nitrates because 99% of the nitrates are all soluble in water. So if I dissolve it in nitric acid, it's easier to do the analysis.
Organic solvents is told in one of your lectures that it has higher sensitivity.
Correct, because organic solvents will burn with exothermic heat. So the atomization temperature increases. The concentration of the atoms in the vapor also will increase. But organic solvents, you have to be very careful because uncontrolled burning might take place. PJ, the student, right?
ಅದು ನಾವು ಹಾಕಿರೋದು ಸರ್. ಸರ್ವೇಶ್ ನನ್ನ PC
PJ.
ಪ್ರೊಫೆಸರ್ JR ಮೊದಲು ಇದು
Oh, short. many students are there? Join bidding. At 4 o'clock countries are there.
ಹಾಂ ಸರ್ ಮತ್ತೆ NPTEL ಮತ್ತೆ ಇಬ್ಬರು ಪ್ಲಸ್ NPTEL 2 ಆಫೀಸ್ ನಾನು
ನಾಲ್ಕು ಇದಾವೆ. 1, 2, 3.
NPTEL
ಕವಿತಾ.
NPTEL ಹೋಸ್ಟ್ NPTEL ಆಫೀಸ್.
What I will do is do a short analysis of the board. What we have done afterwards, we have for the sake of the body, somebody wants to refer to it later. Hello, Maya. Maya.
Yes, sir. Yes, sir.
ಯಾಕೆ ಬಂದಿಲ್ಲ ಶುರು ಮಾಡ್ಬಿಡ್ರಣ.
ಹಾ ಸರ್ ಶುರು ಮಾಡಿ ಸರ್, ಯಾಕಂದ್ರೆ ರೆಕಾರ್ಡ್ ಆಗಿರುತ್ತೆ. ಸೊ ಸ್ಟೂಡೆಂಟ್ ಆಮೇಲೆ ನೋಡ್ಬೋದು ಸರ್ ಅವ್ರು.
ನಾನು ಅದೇ ಅನ್ಕೊಂಡೆ.
ಹಾ ಸರ್, ಒಂದ್ಸತಿ ನಿಮ್ದು ಆದ್ಮೇಲೆ ನಾವು ಕ್ಲೋಸ್ ಮಾಡೋಣ ಸರ್. ನೋ ನೀಡ್ ಟು ವೇಟ್.
This is Mr. Mudakavi. I have been offering this course, atomic absorption spectrometry, since last 20 years. And for the first time, we are offering a repeat course of atomic absorption. And it has been a great journey for us, starting from introduction to the atomic structure onwards to the application of environmental materials, the technique of atomic absorption spectrometry. What we have done in this course is to try to introduce all the participants to a beautiful technology, that is state-of-the-art technology that involves the atomic absorption spectrometry. And as you all know, there are students in this course coming from engineering background, science background, and non-science background also. Many of them are officials in central government and state government, pollution control, and there may be many people who are not in the academic field at all. At the same time, there may be many people who are students and who would like to know more and more about the technique because it will help them either later in their career or elsewhere. I have here with me Pratyusha Chanda, who is a PMR scholar, and say hi, Pratyusha. And this is Sarvesh. Hi. Uh, we have been together since last 2-3 months to offer this course. And what we have done actually in this course is to introduce you to the people from different backgrounds to the technique of atomic absorption spectrometry. That is why we try to uh, avoid the technical we try to avoid the too much technicalities in the in the course, but at the same time we have to appreciate that any scientific endeavor without the attendant problems will never lead to the understanding of the topic. That is why for this course, I had to introduce a few problems as and when required and or as and when I felt essential. So in this course, what we have done is to introduce you to the people, to the science of atomic structure first. We have looked at the components of atomic structure, that is protons, neutrons, mesons, and then electrons. The arrangement of the protons and neutrons in the nuclear structure, that is part of the introduction to the atomic structure. And after we had a fairly clear understanding of the atomic nucleus, we have concentrated on the distribution of the electrons that is around the nucleus. That is the electronic arrangement of the of all the elements, something related to periodic table. I have introduced you all to the quantum mechanical theory and how the electrons are arranged around the nucleus. And as the complexity of the nucleus increases, that is by increasing the protons and neutrons, how we end up with different kinds of elements, and these elements, how they are organized in the periodic table. We have spent some time in that. And with that background, we have defined the periodic table, isn't it? So after the periodic table, I have tried to introduce you directly to the technique of atomic absorption, and I have taught you the basics of spectroscopy. So in the basics of spectroscopy, what we have done is we discuss about the origin of the atomic spectra, how the electrons get excited by the application of energy, and what happens to the excited electrons, and how we can introduce, how we can actually use the movement of the electrons from lower energy levels to the higher energy levels. And after that, we have discussed the relative theory of atomic absorption, that is Fraunhofer lines, and how the Fraunhofer lines in the solar spectrum can be related to the presence of elements on the Earth by comparing the excitation spectra and absorption spectra of the elements in the sun to those of the elements that are present in our Earthen atmosphere. The atmosphere means it covers air, water, as well as the soil structure. That is the whole of the earth. So I have taught you that most of the elements that are present in the earth's crust, at least earth's crust is what we are talking about, and in the oceans and in the air. These are the constituents. They contain all the elements that we normally deal with, which are approximately about 53 elements in our day-to-day life, and how these elements can be determined using atomic spectra. I have taught you that the excitation of the electrons to the next higher energy state can be brought about by heat or some other technique, like hollow cathode lamps, etc., which will interact with the electrons and then help them to get into higher energy states. So when the higher energy state electrons come back to the ground state, they lose the excess energy. If the excess energy is lost by the emission of radiation, then we have atomic emission. But if the excess energy is lost by some other means, probably by collisions along with the neighboring elements, etc., we do have the intensity of the same radiation coming down than what we have actually employed. So the difference between the top excitation and what remains when they come back to the ground state is what is the defined as atomic absorption. So in atomic absorption, what we are looking for is the number of atoms in the excited state to the ground state. So the ratio will be the determining factor that will help you to estimate elements in different concentrations. So if an element gets excited at very low temperature, for example, lithium, sodium, potassium, and these things, we don't need such high instrumentation as has been taught. Yeah, a simple burner like what we use in our kitchens, etc., will help us to convert most of the elements at higher energy levels, approximately of the order of about 10 raised to minus 4 percent into the excited energy level. But the same temperature that we get in our cooking gas, etc., will not be enough to excite all the elements to appreciable concentration to the next higher energy level. Plus, there is also another consideration that the excitation energy and the emission energy, when they match, then only the absorption of radiation takes place. Okay, so the concentration of the element is a relative technique. That is, it's not an absolute technique. What do we mean by a relative technique? A relative technique is one where we prepare the standards and see the response. So we have established that every element has got a resonance spectral line, which is useful for the determination of that element at the lowest energy level, that is resonance line. So we always look for the energy of the excited state at the lowest wavelength. So almost all the elements that we try to estimate are in the UV region, except sodium, potassium, etc. They are in the mercury, they are in the visible range. You see the mercury light, etc., in the road, on the streets. You see the sodium vapor lamp in the streets, isn't it? They are all emission wavelengths, not the absorption wavelength. But if you want to look at the absorption of these things, go and observe the same street lights carefully. When the lamp gets heated, it absorbs its own radiation and lamp puts off. After some time, when the temperature comes down, again the concentration of the excited atoms increases and then absorption takes place. So if you see sodium vapor lamps in any of the, wherever you are, they are there, that if the temperature increases, you will see that the lights are coming on and off, on and off. This is the technique what we have used for background correction by artificially increasing the concentration of the atoms by giving very high current. That is Smith-Hifge and background correction technique. We have the basic instrumentation that has been defined. Now, what are the things that we need basically? I need a sample and I need a radiation source to get the resonance line. So the best way to get the resonance line is to make the same lamp what you want to determine. If you want to determine iron, make an iron lamp. If you want to determine tungsten, make a tungsten lamp. So like that, with each element, we need a radiation source. So a radiation source is nothing but basically a bulb made of the filament of the same element that we get it. But there is a catch because if most of these radiation sources should not be exposed to higher other gases that are present. That is why we need vacuum tubes, almost of the order of about 10 raised to minus 5 atmospheres. Okay, so part of the instrumentation, it starts from the hollow cathode lamp or EDLs, that is electrodeless discharge lamps, or we can use lasers, or we can use some other source also, plasmas, etc., as the initial radiation source. Now, if the resonance line is the one which is useful in the absorption of an element, what about the radiation coming from other sources? Now, we will have to, whenever I want to excite the sample, I provide heat. So many other elements get excited. They may emit radiation. So that we don't want. We want only one wavelength, that is resonance line. That I am providing from the hollow cathode lamp. So whenever the hollow cathode lamp passes through a cloud of the atoms, and then the absorption and excitation and everything is there. So I need a source of the atoms in the vapor state. Now, in the vapor state, I don't need ions. I don't need molecules. I don't need the cations. I don't need the anions. I don't need any other material except the element in its original form. That means the atom should be there in the electronic cloud on the path of the radiation. So then only it can absorb the resonance radiation and go to the next higher energy level, comes down. So I need an instrument. As part of the instrument, I need a background correction. Otherwise, even though atomic absorption as such is basically a specific technique for a particular element, because of the presence of other materials in the flame, from the matrix, from the solvents, from the other elements, I need a background correction. So this background correction we are providing by the hydride this deuterium background correction with heat correction, and I have spent a lot of time in teaching you people about the Zeeman effect background correction. These are some of the best techniques that we have to make the atomic absorption a wonderful technique which is very, very specific to the element that we want to analyze. As of now, we do not know any other way to determine the atomic concentrations at that level. Now, what are the levels we are talking about? We are talking about parts per million, parts per billion, and parts per trillion. That is 10 raised to minus 12 quantitative. Now, there are the improvements have come from instrumentation, background correction, Smith, then Zeeman effect background correction, pyrolytic graphite concentration, tubes, and also with the automation. So the part of the instrument is optics. Apart from that, I need a source for making the atoms. And that means I have to take the sample and convert them into atoms. So I need a nebulizer. So the job of the nebulizer is to split the sample into small droplets, which the moment they enter into a heated zone, they dry up and provide you the solid crystals. These crystals will decompose at the heat provided, and they ionize and then pick up the electrons from the source, from the flame, from the other material, they become atoms. So the importance of atoms in the atomic cloud is very critical. So if you want to improve the atomic absorption sensitivity, you want to determine as low as possible. Now imagine you have a person who is suffering from Alzheimer's disease. So what happens? He has some aluminum in the brain. Now, if you want to determine how much he has gone into the Alzheimer's disease, you should determine the aluminum in his brain. You can't take out half of his brain to test for aluminum. You need a few, you can get a few milligrams. In those few milligrams, instead of 10 raised to minus 12 ppt, it will become 10 raised to minus 18, because if you have sample in grams, you can determine in parts per million, micrograms. If you have sample in kilogram, you can determine in percentage or whatever it is. But if the sample itself is so less, 10 raised to minus 12 of that material, that is the challenge. So what happens? Here in atomic absorption, we are looking for materials, something similar to a needle in a haystack. A needle in a haystack is easy to find. But if you want to find out how many needles are there, that is the challenge that this atomic absorption provides for you. So the beautiful arrangement of increasing the sensitivity, what we need is increase the sensitivity. That means you have to go down to determine the lowest concentration. 10 raised to minus 6, minus 9. Next step was minus 12. Next step was minus 15. And that is the femto level. So beyond the femto level, you have not been able to go down, because the system requirement will become so harsh that there should not be the environment of the instrument location itself becomes so critical that it becomes impossible to go for that kind of background correction. Okay, so the best improvement that have come in atomic absorption, which I have already taught you, is the introduction of graphite furnace. In the graphite furnace, what do we do? I make a small graphite furnace using a graphite tube. It will be about 5 centimeter length, about 2 mm or 3 mm dia, and with a small hole on the top. And I have to introduce the sample into the tube, heat the tube. So instead of using a flame which is very turbulent, engineering, speaking from engineering principles, it is all in the controlled atmosphere now, in a tube, very small tube. I just put it there evaporate the whole lot, and the whole vapor is contained in the tube. Now, if I pass the radiation through the tube, then the atomic absorption will be much better. That is how we have improved from microgram to nanogram and picogram levels. Labov was the first Russian scientist who thought of this technique and made it work in 1967 up to the concentrations of 10 raised to minus 14 grams. And nowadays, routine determinations of atomic absorption up to 10 raised to minus 12 grams are common. That is picogram level, quantitative, not the qualitative. So, the other techniques, which are sister techniques, you can say, are the hydride generation and cold vapor technique. That also I have taught you in the course. I have spent considerable amount of the material of time teaching you about the instrumentation and other limitations, how we can adopt the atomic absorption instrument to the determination of these elements like arsenic, antimony, bismuth, and then ruthenium, lead, mercury, etc. That is known as hydride generation technique. These elements are special, germanium, selenium, etc., because we need them for our solar cells. We need as pure silicon as possible. That is better than 10 raised to minus 15 impurities, grams. So, atomic absorption is best suited for the determination of these materials. Only limitation what I see is the sample needs to be destroyed. We have to dissolve it. You cannot take a small sample and say determine this non-destructively. That's not possible. So what happens? The distribution of the impurity in the sample also plays a major role. So what happens? Suppose I give you 1 kilo of coal and ask you to determine mercury in that. In in a 1 kilo lump, the mercury may be more on the left side or on the middle or in the side, etc. So I need to take an average. That is the limitation. So in general, but at that level, probably we can live with that. That is why we say that even up to 5% variation in the results are acceptable when you are working in parts per billion or parts per billion level. If the results are slightly different, don't panic. That may be correct value. You may be doing well. But you look at the result, there may be variation. So that is why, as far as possible, we try to automate the whole sample. Suppose you introduce through a pipette the sample. Your hand may be shaking, you may be old, you may be sick. So the dispensing of the liquid in microliters may not be the ideal way. So what we do is we go for a carousel, take the sample, pick it up, and then push it. Every time the sample introduction becomes very, very reproducible. That I have taught you that if it increases automation, increases at least by about 100%, 2%, 2 times the reproducibility. That is very important. I'm going to ask you people in the examination about these things. So I want you to study all these techniques carefully as well as again and again so that you are thorough with the technique. I have also taught you about the cold vapor mercury, which we should not forget. Because cold vapor mercury, you don't need an atomic absorption. Even if you need the beauty of mercury determination stems from the fact that even at room temperature, the concentration of mercury varies between 0.30 to 0.32% in the vapor form. You spill a little of mercury, it will be there all over. That is why mercury is dangerous. We should not allow the mercury to be spilled in the laboratory. So, but if the concentration of mercury is so much, why do I need atomization? I don't need. So the instrumentation becomes very simple. I can buy an mercury determination unit for about 2 lakhs, whereas an atomic absorption unit will cost me about 30 to 40 lakhs. And I don't need a source because the mercury is already available. All I need to do is introduce the sample. The beauty of cold vapor mercury is again established by the fact that mercury forms amalgam many elements, especially noble elements. So gold and other materials, and if all you need is a small piece of gold on which you pass or keep on passing the concentration air saturated with mercury or air containing mercury. So suppose it is less than the detection value, then you can pass more air. It will be held on that mercury amalgam. All you got to do is heat your mercury amalgam, mercury gold amalgam, release the mercury, estimate. So that gives us a beautiful technique to determine mercury anywhere in any concentration. Only limitation is how best you can improve your laboratory conditions to go down to the lowest determination levels. For example, even if I move, as I move around, in my hands I may have mercury at some particular level. In my air, I may have. In the tea or if I drink, I may have mercury. So like that, there are different levels at which mercury can be determined at they do test concentration. That is evident from the Minamata Bay disease that has been determined in the fish gills in Japan. Similar technique has been used for the determination of cadmium. So there also it is its determination levels are in parts per billion. Okay. So much I have taught. Afterwards, what we have studied is how to make an analytical technique for the quantitative estimation of the same. I have taught you about the standardization technique, calibration technique, and many other techniques, bracketing technique, etc., where the sample can be reliably estimated using the available techniques. So, we have concluded our atomic absorption studies with a comparison to inductive coupled plasma atomic emission spectroscopy, which has also gone well to be established as one of the leading techniques in parts per million and parts per billion level. So that is where we have stopped. I have a NPTEL course on ICP also, inductive coupled plasma also. So if you need any further information, you are all my students. I will be very happy to provide you. Call me anytime up to 11 o'clock at night. Afterwards, I go to sleep, and call me after 7 o'clock. Anytime. All my students, I am available, and I will help you irrespective of who you are and whatever you are. Okay. Thank you very much. I am extremely thankful to all of you for joining me in this teaching endeavor that is coming especially after the Teachers' Day. So thank you very much. Have a nice day and have a nice career. All the best.
Okay. Thank you, sir. Thank you.
Chanda?
Thank
You
you
would
very
like-
much, everyone, for giving me the chance to assist
Yeah.
Professor Mudakazi in this course. And yeah, so I learned a lot of new things, and it is exciting. And all the best for your exam.
Thank you all. And dear students, if you have any doubts, you can write it on our forum. We can answer your questions. And this course is already, this session is already recorded, and it's already
Available.
maybe today or tomorrow it will available on YouTube also. So please go and check it once. Thank you.